Okay, hello again. This particular time we'll discuss the application of the moment distribution procedure to the analysis of continuous beams. So when you look at a beam, it's a 3-span beam, span AB, span BC, and span CD. So for 3 spans, how do we begin? We begin first by computing the stiffness for each span. And the stiffness for each span is equal to 4ER over L. And so stiffness is represented by K. So KAB is equal to KBA, BA, which is equal to 4ER over L. The 4 is a constant, the E is a constant, and the R is a constant. So left with only 1 over L. It says 1 over 21.6. Similarly for KBC, the E is constant, the I is constant, the 4 is constant. We get 1 over L, which is 1 over 45. For KCD is 1 over 23. Now, after you should have computed the stiffnesses, the next step is the distribution factors. Distribution factors. And for fixed end, the distribution factor is always 1.00, and we have 2 fixed ends at A and at D. So the distribution factor for AB is 1.00. Also, the distribution factor for DC is 1.00. But you have two supports in the center. Two supports in the center. Support B and support C. So the distribution factor for BA, for the direction of B, is equal to the stiffness of BA divided by the sum of all the stiffnesses meeting at joint B. Distribution for BC is equal to the stiffness of BC divided by the sum of all the stiffnesses meeting at B. Okay? So, we'll come now. We'll look at the first one, which is KDFBA. We know the stiffness for BA from the one at the top, we got 1 over 26, 1 over 21.6, divided by the sum of all the stiffnesses meeting at B, which is the stiffness for BA and the stiffness for BC. The stiffness for BA is 1 over 21.6, and the stiffness for BC is 1 over 45. So when you do that small fraction or a small arithmetic, you get 0.675. Similarly, you go to the distribution factor for BC. You got the stiffness of BC divided by sum of all the stiffnesses meeting at B. So it's 1 over 45 divided by 1 over 45 plus 1 over 21.6 gives you 0.324. Now when you add the two stiffnesses at B, or the two distribution factors at B, you're supposed to end up to 1.00. You can see that 0.6756 plus 0.324 give you 1.00. That's the first check on the distribution table to make sure the distribution factors at the joints are always equal to 1.00. This is the beam. Remember, this is the beam, the 3-span beam, A, B, B, C, C, D. Then we go to prepare the table. Go to prepare the table. And in the table, table is prepared like this. The table. I have to turn the phone in the other direction so that you'll be able to see the entire table. You have the table prepared. I have the joint A, joint B, joint C. At joint A, you only have one member coming to joint A, which is member AB. But at B, you got two members, BA and BC. And at C, you got two members, CB and CD. And at D, you got only one member coming to joint D, which is DC. This next line you see is the fixed end moments that were just computed. Because joint 8 is fixed to the beyond factor for joint A is 1.00. At joint B, we add the two factors, we get 1.00. At joint C, we add the two beyond factors, we get 1.00. Obviously, at DC is fixed, so the beyond factor is 1.00. This next line is the fixed end moment due to the external loads, 30x squared over 12 for AB. Okay, we got minus 388. Okay, plus 38. These are the fixed end moments. You know how to compute them already. Fixed end moment. One is negative and one is positive. You can see all of them. The next fixed end moment is the one due to the settlement. And the settlement at C affects joint B, joint C, and joint D. Okay? Settlement at C affects joint B, joint C, and joint D. So which is delta over L for BC, you get 0.000123. Delta over L for C, you get 0.00047. Delta at D, you get 0.0047. Okay. Now the next problem is how do we begin the distribution? Now, I join A and I join D. The two joints can only receive. They cannot give out. So only joint B and joint C will begin to give out and receive at each joint. Now, when you look at the fixed end moment at joint A, it comes from half of the fixed end moment at joint B. When you go to joint B, you have an unbalanced moment of positive 388.8 and a negative 281.001. Now, when you average these two, you see that the positive moment is in excess. In excess. So you got excess of 108. So at excess 108 is distributed at joint B according to distribution factors. So that 108, when you take 67%, you get minus 72.8. And when you take 32.432%, you get 34.166. And when you add these two, you get it 108. After you have done that, you execute what we call carry over. You take half of the 72, keeping the sign along with you. Half of minus 72 give you minus 36. It goes to joint A. It comes from a member AB. And half of minus 34.9616. Half of that goes to 17.4808. It goes to the next joint, on joint C. And you repeat the same thing for joint C. But joint D can only receive. So you look at joint D, half of 95 becomes 47.66. Keep the signs. Or I will keep the signs. Don't forget the sign. Okay. Keep the signs. Then when you come back to joint B, the moment you have a joint B now is, the moment you have is 16.46 and 7.92. We come from this minus 24.3654. Now, you see the minus 24, the moment I need to put that joint equilibrium is a positive 24. That positive 24, you take 67% of that positive 24, you get 16. And you take 32% of that positive 24, you get 7.90. So you keep doing that until you sum all the moments in the columns. And we know I join B for it to be equilibrium. BA and BC is equal to 0. If you look at the two end moments, they are equal and opposite in sign. Positive 30, 330 and minus 330. Also at joint C, you have minus 176 and a positive 176. You add these two, it's okay, you see. So after summing all all of the columns, you get the final moments, and the moments will be similar to your moment in your moment diagram from slope deflection. Thank you.